Hey everyone, welcome to the first video of Unit 3. We're going to start looking more in depth at some organic chemical reactions. And so that's just what we're going to dive into right away. First is looking at a new reaction, or I guess it's not actually that new, but looking at a reaction in depth for the first time. And so we're going to go over some stuff. Hopefully it won't feel too intimidating, but if it does, if the idea of having to analyze chemical reactions for the first time feels intimidating, don't worry, because I promise you've actually seen most of this stuff already through some of the other pieces that we brought in the previous units. Let's take a look at the reaction we're going to think about today, the addition of HX to alkenes. So we'll start by talking about the overall reaction, or you may also hear me call this a general reaction. And that's not the name of the reaction. When I say this, I mean that this is just an example reaction. I mean that it's like an example or kind of a generic version of this reaction that can represent the same reaction happening for a variety of different compounds. So now I'll give the general reaction scheme that shows how HX is added to alkene. So this is an addition reaction. So I'm going to take my, again, generic random alkene that looks something like this. And now this is not to say that you can only use this molecule, right? It can be any kind of alkene, but this is the simple one that I want to use for this example. You might also see me in a general or overall reaction start using some R groups to say, oh, okay, this R group here could be something other than just a CH3, and this R2 group might be different than R1. So I'm going to leave those off for now just to keep it a little bit more simple today, but hopefully you're getting more familiar with seeing groups like R and understanding that that means some other stuff that we don't care about, but it's not just a methyl group. So if we have an alkene that looks like this, and I'm going to draw in these two hydrogens here just for clarity, and then we have some kind of a halogen acid that we're going to add to that alkene. So those are our, well, this is our reactant, right? That's the thing that we're going to actually do the chemistry on. This acid is what we might call a reagent. Don't get too bogged down in those terminologies. Both of them are reacting partners. And then what's the product? That's the actual part that we're more interested in. So what we'll find for our product is that we kind of end up with something that looks like this. And I'm going to draw a little bit of extra color coding here, just to make it really clear what exactly is happening with these different molecules adding together and the different atoms ending up in different places. And so when I say X, that's any halogen, right? So that can be fluorine, chlorine, bromine, or iodine. And this is just, that's the generic version of a halogen. So we get a product that looks like that. Cool, right? What does that mean? Why do we care about it? That's going to be an important type of reactant for what we're going to talk about in this unit, where we're going to actually look at some applications of organic chemistry to actual things in your real life that you use literally every day. I guarantee it. So that's part of the reason that we care. And then when we're just analyzing these in an organic chemistry setting, we want to be able to think about what's going to happen and, of course, how it happens. So that's what we started looking at the end of last unit. So when we think about how it happened and what exactly is happening, there's some things that you should notice, right? So if we think about where we started to where we ended up, we know that we reacted with that alkene, right? Specifically, I'm talking about that pi bond, that alkene, and we know that because it's no longer there in our product. It's gone, so it's just disappeared. And by disappeared, I mean it's reacted. It hasn't magically disappeared. It's been converted into something else. The other thing that you should notice is that we've made some new bonds, right? So these new bonds that we've formed are to a hydrogen and whatever X is, that halogen X. And that they've been added to sort of either side of our alkene. If we were to give this some numbers, as you know I love to do, We could say this is a 2,3 alkene, right? Because it's happening there between carbons 2 and 3. And then at carbons 2 and 3, we added a hydrogen to one and a halogen to the other. So thinking about what happens over the course of a reaction, or at least what's different, will help you kind of figure out what's happening in the middle. And so that's one of the big pieces, like I've always said, that we really care about as organic chemists, is how this stuff happens. So we love to talk about mechanisms and try to figure them out. And so how do you figure out a mechanism? We've looked at a little bit of practice of kind of just drawing between nucleophile and electrophile, and so we're definitely going to employ that here. But first things first, we want to think about what the components of the reaction are a little bit more, because now you won't necessarily be given the products, and you'll have to kind of think through it a little bit more carefully. So if we look at those components, we're going to have to go back to our practice and decide what is a nucleophile and what is an electrophile. These are going to be a little trickier than what we saw in the last unit, but I promise with practice it won't be too bad. And then if we know what's the nucleophile and what's the electrophile, then that's going to tell us how we have to draw our arrows. So now I'm just going to bring down a copy of our reaction from before. And I'm going to erase the product for now because we want to think about the mechanism. That means we're not even thinking about the products yet. We're just thinking about what we're starting with and what we can do with it. So let's think about nucleophile and electrophile for these two components. And I'm going to actually even get rid of this arrow for now. We'll come back to that later. So between these two, go ahead and pause here and make a quick prediction. Which one you think is the nucleophile and which one you think is the electrophile? And if you're not sure, just keep watching. We'll talk through it together. So just for me, I think I would start with the halogen acid because it's smaller. It seems like maybe that's going to be easier to wrap my brain around to start with. But then looking at it, I'm still not kind of exactly sure, because I'm looking at this H and I'm thinking, okay, that's definitely a partially positively charged thing. We know that H plus, when we have that, that's definitely an electrophile, but we don't have H plus here, so it's not exactly the same, right? So the hydrogen could be an electrophile, right? And so that might mean that this whole molecule is the electrophile. But then we can also look at the X portion, which is some halogen, which we know has 3 lone pairs of electrons on it, right? And we know that lone pair electrons can be nucleophilic. So, this one is a bit tougher than it seems at first glance. So the other thing that you can evaluate is our other reagent here, and that's this alkene. And so that doesn't have any nice, obvious positive charges to make you think electrophile, and it doesn't have any lone pairs to make you think nucleophile. But this was kind of one of the weird, subtle ones that we talked about in the identifying nucleophile and electrophiles video. And this one we ended up deciding is a nucleophile after all. So this one is going to be our nucleophile. And it's not that you're going to have to memorize 8 million nucleophiles. You'll get more used to seeing the patterns as we go along, I promise. So there's our nucleophile, which means that this has to be our electrophile. But again, if you want to be really super clear, let's define the exact pieces of each of these that are nucleophile and electrophile, because that's going to tell us exactly what we need to do with our arrows. So if we think about this whole molecule is our nucleophile, and I'm going to move this around so I can draw a little bracket around it. That whole thing is our nucleophile. But what's the nucleophilic part of that molecule? That is going to be this double bond, or this pi bond, is what's actually going to be the nucleophile. And then when it comes to our HX molecule, what's actually going to be the electrophile? This hydrogen atom is going to be our electrophile, or the electrophilic atom. So if we know this, then that's not too bad. We can go ahead and start drawing some arrows. So with these designations figured out, we can go ahead and just start drawing some arrows. So I'm going to go ahead and bring this reaction back in, but get rid of the product because we're not ready for that yet. We need to show some electron arrow movement to understand how this reaction happens. So in this first step, we're going to reach out with our nucleophile and go to our electrophile, right? Hopefully this feels a little bit more comfortable now with the practice that we started on it during the last unit, but we're going to reach out with our nucleophile, going from the electrons to our target, which in this case is that hydrogen atom. And because that hydrogen already has a bond to it, we have to break that bond because hydrogen only wants to have one bond at a time. We're forming a new one with this first arrow, and so our second arrow, we have to break it. And you don't have to label your arrows with numbers, but if that is helpful for you, absolutely go ahead and do it. Okay, so there's our arrow pushing. And then we have to think, well, like what else? We're not done. Normally when we show a chemical reaction, we maybe do some arrows, we start with some things and we end with some things. So we need to figure out what actually we made here. And that piece can sometimes be a little bit difficult and intimidating. So here's a couple of steps that you can follow to think about how to draw your new products, the things that you made. So looking for the new bonds that you formed, make sure that those get drawn in. Remove any bonds that you've broken, right? And so we're going to have to do both of those two things because we made a new bond and we broke a bond. And then be sure you're checking for formal charges. Formal charges are one of the things that gets dropped all the time in organic chemistry mechanism drawing. And it's a quick and easy place to lose a bunch of points, right? So make sure that you've got your formal charges all represented just as they need to be so that you don't lose points. So let's think about drawing the new bonds that we formed and drawing the old, or sort of removing the old bonds that we've broken. And if it helps for you to actually just recopy this exactly as it was, we can honestly just do that. And I can do it really quick and easily on my iPad. You're welcome to just sketch it in on your paper, whatever it is you're using. So I'm going to get rid of these arrows because they don't make any sense for this anymore. But the point of copying it over is so that you don't forget any of the other pieces, right? Because nothing was happening, say, with this methyl group here, but that is still important. It needs to be in the product. So we made a new bond from one of these two carbons to that hydrogen. Now here's a question. Does it matter which carbon that hydrogen goes to? And the answer is yeah, it absolutely does matter. But we're going to ignore that just for now for this practice example and put it on just one carbon or the other carbon. So for this one, it doesn't matter, but we will see why it does later on. So I'm just going to arbitrarily pick to put the hydrogen on this carbon here because that's the one that I did put it on in the general reaction. So I'm going to go ahead and do that momentarily. But before I do, I want to also remove the bond that we broke. We broke this pi bond in order to form that new bond, right? So I want to remove that first because otherwise, if I don't, I'm going to end up with a bad situation where I have 5 bonds to carbon and then you all will make fun of me. And I don't want to have that, right? So I'm going to remove that first and then add in that new bond to hydrogen. Okay, and so now that hydrogen has been scooted over to the carbon. And we had to break that HX bond. So that's what I just did. I just erased that bond. And so now we've broken all the bonds that we needed to break. We formed the one new bond that we needed to. And are we done? No. You got to check for your formal charges, right? So does a halogen atom just kind of hanging out by itself have a charge? Absolutely it does. Any halogen without a single bond is going to have a negative formal charge. Remember that it had 3 lone pairs of electrons to start, and then the 2 in this bond kind of scooted over to hang out with that halogen as well. So now they're there. Okay, and so think about your charge balance. If we have a negative charge on this side, but we have no negative charges over here to start, it's not balanced. So we need to balance the negative charge out with a positive charge. Where might that be? Well, we can think about what we did with this alkene here and say, yep, we used this alkene to reach out and make that new CH bond. So the electrons that are in this pi bond right here actually end up in this bond. That's why I've kind of color-coded the bond as black to match up with the black alkene electrons. And so we kind of took the electrons away from both of these carbons at the same time. But if we look at where our product is, this carbon gets to keep those electrons, and this one kind of lost out on and got the short end of the stick, right? So if we are less one bond here than we need to be, that means that we don't have a full octet. We have only 6 bonding electrons, and we need a positive charge at that carbon. So sometimes it can be a little bit hard to just see without looking at the halogen that we need a positive charge there. But that's why I want to encourage you to use things like the counterions, like halogens, to remember that we need to have a charge balance here in order for this to be a full, correctly written out product of this first step of the reaction. So that's what we've made. And are we done now? No, not quite, right? Because if we think about, I'll repaste it in here quickly, the product of our reaction is a product where we have this new halogen to carbon bond formed, but we haven't done that yet. So that means that we can't possibly be done with this reaction. So there must be at least one other thing that we need to do in order to get to our final product. So what we have right here are what we would call intermediates, because they're not exactly the same as what we started with, but they're definitely not the final product yet either. So let's take our intermediates and let's copy these down to our next slide and figure out what it is that we need to do with them. So we made these two new things, these intermediates, and now they need to somehow react together in order to hopefully get us to our final products. But what do we do? How can we tell what else needs to happen? We used a little bit of our intuition and some things that we learned in last unit to decide, okay, what had to happen in the first step, but what has to happen in step 2? Well, we can go about the same process here to decide what's our nucleophile, what's our electrophile, and then just draw the arrows that follow from those decisions. So let's look at these two pieces now and see which one looks like what. So again, maybe start with a smaller one. This one is just a halogen atom with a negative charge. If we think about that, hopefully that's a little bit more clear and easy than it was before. There's only that single atom and it has a lot of electrons. So this is definitely going to be our nucleophile. And so by extension, that means that this molecule has to be our electrophile. But let's get down to the nitty-gritty of it again. What part of this molecule specifically is the electrophilic atom? Hopefully it's pretty clear with this positive charge. We should be thinking about that area there, which has the positive charge on it. And specifically, that means this carbon atom right there. So if that carbon atom is our electrophile, and give that a little circle to remind us that that's our electrophile, we just need to go from nucleophile to electrophile, draw our arrows, and then that should be this step taken care of. So let's go ahead and draw those arrows in and see how we look. All right, so I'm going to use a pair of electrons from our nucleophile. It doesn't matter which one. You can use any of these 4 pairs. I'll use this one since it's a little bit bolder than the others, just for emphasis. So we'll draw from that pair of electrons, and we're going to go right straight over to that carbon. And so we can think about, do we need to draw another arrow here? And the answer is that we don't, right? Because we're not removing this hydrogen. We know that ends up in our product. And we know that this carbon, because it has that positive charge, is missing some electrons. It doesn't have its full octet. So it's able to accept some electrons without needing to remove any other electrons or break any bonds. It can just pull those electrons in and form a brand new bond. So then we have to kind of figure out, okay, well, we did another thing here. What is our product? What did we just make? So I'm going to recopy these pieces over again. Get rid of our arrows and all of our other little weird shapes and think, okay, so we used these electrons here, those purple electrons, to make a new bond to this carbon. So you can even do that just like this. It might look a little funny, right? But yeah, there we go. That's the new bond that we made. We didn't break any bonds, and then we just have to double check our formal charges. So that's absolutely one way you can do it. I'm going to draw this so that it looks a little bit nicer for the video and say basically, okay, our atom X, whatever that was, had to probably get closer to this carbon in order to actually attack it. So I'm going to draw it closer in and then draw that bond in there in purple. And I'm going to remove this halogen over here because we want to, if you want to do this recopying and then erasing strategy, it's absolutely fine. Just make sure you don't leave anything extra hanging around that doesn't need to be there. Use your eraser as you need to. Okay, so that X had a negative charge before, but now it has 3 lone pairs and 1 single bond, so it's actually happy. And the fact that we used those electrons to make a new bond to this carbon means that it actually has 4 bonds, right? And has 1, 2 with that halogen, 3, 4. So it has its octet now and it's happy again. So the carbon doesn't need a positive charge either. So thinking about just charge balance, we had a negative and a positive here. That adds up to be overall 0 charge. And then we get to this side. Now there are literally no formal charges at all. That's also a totally 0 formal charge. So they have to balance out. Okay, so hey, that with a little bit more annotations than I had before, we can remove these lone pairs. But that's the exact same product that I drew in our sort of general overall reaction. So now we've kind of got an idea of how these steps can happen. Let's just put them all together on one page so that we can see them clearly. And maybe we'll talk a little bit more about what's happening in each step, just to put some words to it. If words are going to be helpful for your learning, we'll add some here. So first we start with our alkene. We have our HX acid, and then we're going to do the same arrows that we did before. We know that this is our nucleophile here. We know that this is our electrophile, so we're going to reach from the nucleophile to the electrophile. And in this case, we need to break a bond like so. And then we're going to draw our intermediates here. And let me fill in these hydrogens too for absolute clarity. You don't have to fill in hydrogens like this that don't react, but you're welcome to. I think it helps me to be able to keep a little bit closer track of where the atoms are all ending up, and reminds me to think about, okay, this carbon had a double bond before and it had sort of 3 things bonded around it. It was sp2 hybridized. And over here, it's got the same number of bonding partners, but it's missing some electrons, which means that it needs a positive formal charge to it. Okay, and let us not forget that we also have this X minus hanging around after the end of that first step, and we formed our intermediates. And then in our second step, we can use our newly formed nucleophile to reach out and attack at our electrophilic carbon. And that's what forms our new carbon to halogen bond that we see formed in our product. Just like so. Okay, let's put some terminology in here. So the first step is what we would call a nucleophilic attack. You'll often see me abbreviate this as NUC attack for nucleophilic attack, but without having to write out the whole word of nucleophile. The other thing that's happening here is the alkene is just kind of picking up the hydrogen using its electrons. Those are the 2 kind of ways that you can describe what's happening in this first step. One is the kind of more chemistry technical term, or you can use these sort of more wordy descriptions to say, yeah, the alkene is reaching out, picking up a proton, and then we're forming these intermediates. We won't necessarily always form an intermediate when we look at some different reactions later this unit, but sometimes we do. And in this case, we do. Then the next step, and if we look at the next step and thinking about what we're doing here, it's actually very similar to what we did in the first step. We have a nucleophile and it's going out to attack an electrophile. And that's really the basis of all organic chemistry. Sometimes we'll have slightly different names for it, but if we think about it, this is exactly the same in that it's just another nucleophilic attack. We maybe have a different nucleophile and maybe a different electrophile, but that's all that's happening. We have a nucleophilic attack of a nucleophile to an electrophile. So the other sort of more wordy way that you could say this is that the halide or halide anion attacks the carbocation. So I'm just going to call it C plus for now, but we'll talk about what that C plus is and the other word that I just used there in a moment. So we're going to attack at that C plus center. And then at the end, our products are formed. Yay. So you may see me start to put these labels on as we start to learn new mechanisms. You don't necessarily need to do this for yourself. If you find it useful, go ahead. If you don't find it useful, don't waste your time writing it. It is whatever is going to work best for you. So let's walk back for a second to that C plus, and I let slip a strange word there. And what was that? I said carbocation. And so carbocation, I feel like kind of makes sense when you hear it, carbocation, but students often just their brains get confused because the English language is the worst. When they look at this, they see cation like vacation. That's not how you pronounce it. So just a little bit of, not nomenclature here, but the pronunciation guide is to think of it like carbo, like when you eat a lot of pasta, carbohydrates, and then cat, because who doesn't love cats? Cats are the best, sorry dog people. And then ion, because it is an ion. So a carbocation is just a carbon that is missing its octet. Right, so I alluded to that earlier, thinking about how many electrons were around that carbon. We said, oh, we lost some, it's only got 6. If it's got 6, it's missing its octet. And if that's the case, that carbon has to have a positive charge. So we discussed this a little bit at the very beginning of the semester when I showed you that formal charges chart, that when carbon has only 3 bonds and no lone pair, it has to have a positive charge. And so this is just the fancy organic chemistry term for that type of carbon, is a carbocation. And we have to think about some of the stability considerations when we're thinking about something that has a positive charge. So if we're missing our octet, that's not good. We wanted to get to octets in Gen Chem when we were drawing Lewis structures, right? Having no octet or having a missing octet, missing electrons, is unstable. So we don't like that. And if something is unstable, so the carbocation itself being unstable, that means that it's hard to form, right? If there's something that is unstable, right? So I'm thinking a lot about doing yoga at home, right? If you're trying to balance on one leg, there's not very much stability there. And that makes that a really hard pose to achieve, right? So thinking about it that way, that it's just gonna take a lot more energy to do this thing that's hard to do. And so that will help us remember that in order to make this carbocation, which is unstable and kind of unfavorable, we need to add energy, which means that that first step of the reaction is endothermic. And so that's kind of our first consideration, is if it's unstable, it's hard to do, and that means we need energy. The second consideration is if something is unstable, then if we still want to do it, we have to find ways that are going to be able to make it more stable, because then it'll be easier to do. So there are going to be 2 different types of stabilization for carbocations that we'll learn about in this unit. We're going to focus on one today, and then we'll learn about the next one in the next lecture video. So when we form a carbocation for the first time, we want to do it right the first time. So essentially, when we're doing this, we want to form the absolute best carbocation that we possibly can. And so the best type of carbocation, well, so what does that mean? What does it mean to be the best carbocation? We're going to explain that in a little bit more depth here in a second. But for now, suffice it to say that the best types of carbocations may be unstable, but they get by with a little help from their friends. And by that, of course, I mean neighboring carbons that are nearby, which can help lend a little bit of stability. So let's start looking at a carbocation, shall we? So there's a carbocation. Pretty exciting, right? It's just a C that doesn't have its full octet. So I'm drawing it like this with some wedges and dashes to just kind of show an arrangement in space. So just as a little refresher, if we have, say, an sp3 hybridized normal, neutrally charged carbon, that looks like this, and that has a tetrahedral geometry. But if we have a carbocation, it's missing some bonding partner. And because it's missing one of those bonding partners, it only has 3 things around it. So that means that it's sp2 hybridized, right? And if something is sp2 hybridized, that means it takes on a trigonal planar geometry. So I'm trying to kind of show that here. That's my really bad drawing of a plane in perspective to show that these hydrogens are all sitting in a same plane. They're kind of like, you know, blades on a 3-bladed fan. They're all in the same plane together. The other important piece that I love to draw on these molecules is that other thing that's there, right? So if we think back to our hybridization, if we have an sp2 hybridized atom, that's cool, it's got 3 bonding partners around, but then what happened to that other p orbital? It remains there unhybridized. So we can draw that as kind of a funny teardrop shaped lobe, both above and below the plane of that kind of fan of hydrogen atoms. So the way I like to think about this is that the positive charge is kind of sitting inside of that p orbital. It's not exactly the case, but that'll work for our assumptions for this class. Is you can think about that p orbital being empty or that it's holding on to a positive charge. Either way, whatever makes the most sense to your brain, right? So knowing that there's a positive charge either on that atom or inside of that p orbital, we know that this is an electron deficient species. Just meaning that it's not got its full octet. It wants a full octet and it just doesn't have one. So it's deficient in electrons. So the instability of the carbocation comes from the fact that it's electron deficient. So if we wanted to stabilize it, we just need to add some electrons to make it a little bit less electron deficient. So when we talk about getting by with some help from its friends, it would love to get some help from these hydrogens, but those hydrogens don't really have any spare electrons to help donate to this carbocation. The only electrons that they have are featured in these single bonds that are already made to that carbon. So they can't give those electrons to the carbon anymore. They're already sharing them. So that means that this particular carbocation doesn't really have a whole lot of help from its friends to stabilize it. But let's draw a different one that will maybe be a little bit better off. So we'll draw a very similar looking one, except I'm going to change one of these hydrogens to a CH3 group. And again, just drawing some wedges and dashes there, not because there's any chirality to this molecule that we need to worry about, but just to show their positioning in space. So if we have a neighboring carbon, now that carbon has a little bit of electron density that it can help kind of donate to our deficient carbocation, but not through like a pair of electrons. It's going to be through these actually bonding electrons of the carbon and hydrogen. So how can this happen? The thing that will be helpful to picture, and I'm going to redraw this quickly, is thinking about these bonds here. Not just think about them in terms of, oh, it's just a straight bond, or it's a wedge, or it's a dash. Think about them as actual orbitals that take up space and hold electrons. So this can be a lot as far as just processing and visualizing. So I'm not going to be asking you to draw any pictures that look like this. This is just to help your understanding. All right, so if we think about the hybridization of this CH3 group, it's an sp3 hybridized tetrahedral molecule. So that is going to be made up of these sp3 orbitals that have kind of one big lobe here, and they have a little baby lobe that kind of points out the other end, right? So it's not like this p orbital that has two even lobes. There's a big lobe and a little lobe. And then that interacts with the s orbital of hydrogen. So there's our hydrogen atom s orbital. And the overlap between those two is what holds that pair of electrons that forms the CH bond. So that's just a quick reminder of kind of the structure of bonds from maybe back in Gen Chem you learned this. That part is not so important. The part of how they are arranged in space is important. So this is kind of relating back to thinking about like the Newman projections that we just did in the last unit. The arrangement in space of this bonding or interaction and this p orbital are aligned exactly so that they can actually overlap a little bit. So if we think about the way that this bond was drawn before, this bond was drawn as a straight line bond, meaning that it's in the plane of the page. This p orbital here, being kind of drawn straight up and down, also means that it is in the plane of the page, whereas these other hydrogens are shown coming in and out of the page. So if these two things are aligned in the plane of the page together, that means that they can actually just, have a little bit of orbital overlap, like so. And now this doesn't mean that we've made some kind of a pi bond, not at all, because this interaction that's happening is very fast and only temporary. And the reason for that is because we have free rotation around that carbon-carbon bond. So it's not like this CH bond is always interacting with that carbocation. So it kind of interacts for a moment and then it's done. So the way that I like to think about this is that this is always rotating and we have orbitals with this hydrogen and this hydrogen that are doing this exact same thing, but basically in a kind of a windmill high five manner where this carbocation is kind of, that's always here. Let's just pretend that that's totally static and not moving at all. And then we have one of our hydrogens, say it's this one, kind of rotates up into the plane and gives that carbocation a little high five, of electron density, and then it kind of keeps going, right? Windmill high five style, where you really like swinging your arm really big. But then after that high five happens, one of these other hydrogens rotates up, gets into the position where it aligns with that p orbital, and it gives that a high five. So you kind of have these repeated high fives happening over and over again while this bond is rotating. This high fiving is the kind of the motivation from its carbon neighbors, right? It's giving it a little bit of a high five, just, hey, yeah, I'm here. I know you're struggling right now. You've got a little bit less electron density, but I'm pulling for you. Give them a little high five. This high-fiving behavior is what we call hyperconjugation, and it's incredibly important for stabilizing carbocations. So the term hyperconjugation, you don't have to be worried about where that term is derived from or exactly what the conjugation part. Don't worry so much about that. Just know that it means these little high fives of electron density going from neighboring carbons to a carbocation. If you have hyperconjugation, that's good, but the more you can have, the better. So let's look at a stability trend for carbocations. We can have 4 kind of different classes of carbocations based on what else is around it. So the first one is just a CH3. That's the smallest carbocation you can have. That's the first one in that sort of first example that we looked at on the previous slide. It's a CH3. So that is going to be on this least stable end because it has no hyperconjugation to it. The next is if we add 1 carbon, 1 CH3, and then there's 2 other hydrogens there. Now we have a little bit of hyperconjugation. We can keep going and just add more and more hyperconjugation as we go along. So if we have 2 methyl groups and 1 hydrogen, that's pretty good. But better yet is if we can have 3 carbons around so that they can all donate a little bit of electron density in at a given moment so that our carbocation doesn't feel so unstable. So let's put a little bit more terminology down here to these sort of carbocations and their names and some ways to describe them so that we can talk more about carbocations that are, maybe we're going to see that are different. And so I should say this is, again, a general stability trend for carbocations. And that means that these don't necessarily have to be methyl groups. They could be other carbon groups as well, but methyl is just one of the smallest, easiest groups to draw. So that's why I've chosen that. So speaking of methyl, right, this, if you have a CH3 in any capacity, we call that a methyl. So this is a methyl carbocation. But what is it called when we have a few more things, right? So you could think about CH3, CH2, that's kind of like ethyl, but we're not going to call it that because it won't always be 2 carbons. It could be many more than 2 carbons. But if we think about how many sources of hyperconjugation, how many neighbors are here to support this carbocation, we would see that it's 1. So we think about calling this a 1 prime, right, or primary carbocation, because this carbon that we're looking at, the one that has the charge on it, only has 1 neighbor, right? So this is a primary carbon and a primary carbocation. And then this can go along, continuing the trend. If we have 2 neighbors that are able to help stabilize, that is a secondary carbocation. And if we get to the 3 neighbors, we call that a 3 prime. We also call that tertiary, which may be a term that you wouldn't have heard as often as primary or secondary. So if you hear me say tertiary, that's what that means, is that there's 3 carbon groups around a carbocation. If we have a methyl carbocation, that, like I said, is the least stable because there is literally 0, no hyperconjugation. I'm going to abbreviate that as H conjugation, C-O-N-J. No hyperconjugation at all. But then if we go up and up and up, there's plenty of hyperconjugation here. In fact, as much as you could possibly have. Right? So if we think about how this would affect stability, the more hyperconjugation that we have, the more stable that positive charge, right? Because the nature of the positive charge isn't changing. It's just what's around it and how much that can contribute to its stability. If it's just hydrogens, that can't really contribute. If it's carbons, they actually can contribute. So if we're thinking about how stability goes, stability is going to increase going in this direction. And the stability of a carbocation is so important that if we don't have a stable carbocation, it's just not going to happen. It's not going to form. It would rather just not do the reaction than try to make something that's so unstable. So because there's literally no stabilization available to us for the CH3 group, it's literally not going to happen. So you will never see this methyl carbocation. And then the same goes for primary. There's a little bit of hyperconjugation, but it's still not enough. So you will literally never see these react as carbocations. They just will not form. So this will come into some of our predictions about how this reaction is going to happen later on. But you will definitely see our secondary carbocations because these are okay carbocations. And you'll definitely see the tertiary because these ones are the best carbocations. Now that we know a little bit more about what makes a carbocation stable in and of itself, we can be a little bit more picky and choosy about how we complete our reactions. So let's go ahead and look at a couple of examples to kind of practice thinking about what's the best carbocation. And then this will help you to predict the outcome of reactions later on. So we're going to start with a couple of alkenes here, and we'll just go one by one, practice drawing some arrow pushing, and think about what carbocations we could possibly make and which one we should make. So let's start with this very first one here and draw some arrows. So I've just given you a random proton. So this is not the same as the reaction that we were looking at earlier. This is just a random first step of a reaction where we're going to use this proton from somewhere. Doesn't matter where. And so we're going to reach out with our nucleophile because this proton is definitely our electrophile, right? So we're going to reach out from our alkene and pick up that proton. And now let's draw the two possible carbocation outcomes that we have to decide between. So let's break it up into two different ones. So one we could put the hydrogen at that position there, which is purple. So we'll draw that in purple. And then the other possibility is that we could put the hydrogen here at this green carbon, and so we'll draw that in green. So for the first one, let's draw that over here in purple. We have all of those carbons there, and then we know we had to break that pi bond in order to make a new bond to that hydrogen, so we don't have that pi bond in here. And we decided for the purple one, we were going to put that new hydrogen at this position, right? And so that means by extension, the carbocation has to go there. Right? And that's one option. Now let's look at the other option in green. Again, same carbons, they're kind of arranged in the same way, but now we're putting the proton here, which means that the carbocation has to go there. So real quick, answer the video question, which of these two carbocations is the best possible carbocation, green or purple? If you're not sure, let's analyze. So looking at both of these, we may want to try to put that kind of name to these carbocations to decide, is it the ones that we're never going to see, methyl or primary carbocations, or is it a secondary or tertiary? That way we can decide which one is the best because we know tertiary is the best. So if we look at this purple carbocation here, we're focusing on this carbon right here in the center. So we want to look and see what's around that. Looks like we have a CH3 group here and here. And then this isn't a CH3 group, but it's another carbon group. So that can also hyperconjugate in the same way that we drew before. So this seems like it has three groups around it. So this we would identify as a tertiary carbocation. Okay, that seems pretty good, but let's check the other one just to make sure. If we're now looking at this carbon here, this one, I'm going to draw a little black dot there to remind us that that is the one that we're looking at. And then think about what else is around this carbon here. So we definitely have one CH3 group available to us here. We have this big group here. So that's two carbon groups. But is there anything else? The only other thing that remains there is one single hydrogen, right? We didn't draw this in earlier, but it is there. It's right here on our original structure, but that hydrogen can't donate any hyperconjugation effects because it's too small. It doesn't have any spare electrons that it could share. So that isn't going to contribute to hyperconjugation at all. And if we're just looking for carbons, we found all the carbons that we have. There's only two carbon-based groups remaining there. So this is a secondary carbocation. So now, hopefully it's clear which one we want and which one is the best. We want that tertiary or purple carbocation. And so we're going to say, no, thank you. That carbocation is not good enough. So this is an important step for you to do while you're predicting these mechanisms of additions of HX across an alkene, because you will have two options every time of which carbocation you want to make. You always, always, always want to make the best one. So if you can just kind of see it by looking at this molecule over here and say, oh yeah, okay, I know which end I want to add that hydrogen to because the positive charge has to go to the opposite one, that's fine. I think it's definitely helpful to draw out both options so that you can evaluate them carefully and then decide which one is better. So use whichever method works the best for you. Let's try this next example. Again, we have another alkene, so there are always going to be alkenes for this, and we can just decide, okay, let's maybe decide between the blue end here, and we'll make the other end orange. So same arrow drawing is going to happen here. Our alkene is the nucleophile. That's what's going to reach out and pick up the proton, but I definitely recommend you drawing these in for your own personal practice. Now let's try the blue one first. So we'll draw in all 4 of those carbons, and then we're going to add the proton here at the blue position. And then that means that the positive charge has to go to the other side there. So we'll see about that, and then we'll draw the orange one as well. And now we decided that for this form, we want the hydrogen to go to that central carbon, and the positive charge would then come out here on the end. So quickly answer the video question. Which one do you predict is going to be the most stable carbocation? The blue carbocation or the orange? This may be a much more obvious one, but just in case it's not, let's walk through just like we did with the other examples and define the sort of names of these types of carbocations. So starting with the blue, let's look for carbon groups around that carbocation. We have one here, we have another one here, and then we have this H up here. That's another methyl group that's just got that one hydrogen drawn in just because that's the position we wanted to show it being added to. But they're all methyl groups. So 3 methyl groups. That seems like it is also going to be a tertiary carbocation. Seems pretty good, but let's look at the other one just in case. Now, if we're focusing here on that carbocation sitting at the end, that has this adjacent to it, but nothing else really. At the end of this alkene, there are 2 hydrogens to start with. So there's 2 hydrogens here, but no more carbons, right? And so if there are no more carbons available to us, that means that we only have a primary carbocation. And we said that primary carbocations are so bad that they're not even going to happen. They just literally will not happen. So we can definitely strongly rule that one out straight away. That is not going to happen. We are only going to form the tertiary one because that is the most stable. So I happen to pick examples that both make tertiary carbocations here, but they don't have to be tertiary. They just have to be the best one possible. If you had primary versus secondary, the secondary would still win. So let's look at this very last example here. And let's decide here between pink and what other color do we want to use here? Maybe just gray, which is not really a color, but it'll do for a highlight. So we'll go for pink and gray. Same idea, let's draw our arrow just to practice our arrow drawing artistry. There we go. And then we can add it to either one side or the other. So we'll draw the pink one in first. That looks like this. And so this is actually the representative molecule that we used in the original example. If we put the hydrogen there, the positive charge has to go with that carbon. And then let's draw the gray version here, where the hydrogen goes to that position, and the positive charge goes to the other side. So quickly answer the video question, which of these 2 carbocations is the best, pink or gray? And hopefully you're really mad at me for asking that as a video question, because this is a rigged choice, isn't it? If we look at what the substitution is around either carbocation, let's start with this one here. We have 1 carbon group, 2 carbon groups. If we look at this one, we have 1 carbon group, 2 carbon groups. So the fact that they both have 2 carbon groups around them means that they're both secondary carbocations, and it means that they're equivalent. In fact, they're actually the exact same molecule. If you took this and just flipped it over, rotated it 180 degrees, it would be exactly the same thing. So these two are equivalent. There is no choice. They're the same. And so I won't ask you a question like that on an exam or anything. This is just to prove the point that sometimes you might be able to make two carbocations that will end up being the same stability. So you can make either one and it doesn't really matter. Okay, so with that, hopefully that clears up what I mean by best carbocation and give you a way to try to decide between the two of them by drawing them both out at the same time. So let's look at a little bit more practice here as far as drawing some mechanisms, and we'll predict the outcomes of some reactions coming up as well. So let's practice drawing the mechanism for this reaction. When I ask you to draw a mechanism, I want you to show me each and every step of the process, and I want you to show me all of the arrows that are required to show the electron movement here. So when you are asked to draw a mechanism, you will be given the thing that you start with, you will be given where you end, and you have to show me the process to get from A to B. So let's get started by drawing out the first mechanistic step of this reaction. I always appreciate if you redraw molecules like HBr to show that bond, because in our first step, we're going to need to break that bond. And so I want to see any of the bonds that you're forming and breaking clearly and explicitly drawn out. We're going to start from our nucleophile and go to our electrophile, as we always do, reaching out to pick up that proton. And then we have to break our H to Br bond, because hydrogen can only have one bond at a time. And so it needs to break that bond to bromine. Okay, so what are we left with? What are our intermediates going to look like? Well, we're going to have all of these carbons here. So I'm going to draw that same carbon chain shape that has kind of 5 carbons to it, like so. And there's a little methyl group hanging off in the middle. And then we have to decide, where do we want to put that hydrogen? We have 2 options. So let me, in fact, draw both of those out here. And then we can decide which one is best and get rid of the other one. So if we put the proton at this middle position here, and you can, again, give these carbons some numbers if it helps you think through it. It's probably not the best numbering that I could give for nomenclature, but I'm going to just stick with it because we don't really care about nomenclature anymore. We got through that unit. We're going to put that proton at carbon 3, and that means that our positive charge will have to go on carbon 4, or we can do it the other way around. Put the proton on carbon 4 and put the positive charge on carbon 3. So quickly answer the video question, which of these carbocations is more stable? The one where the charge is on carbon number 4 or where it's on carbon number 3? Hopefully seeing these patterns is feeling a little bit more familiar by now, that we need to have more carbon groups around our carbocations to be more stable. So that means that this one with the carbocation on carbon number 3 is more stable because this is a tertiary carbocation, not to be confused with the fact that it's carbon number 3. That numbering is arbitrary. But this one over here only has 2 carbon groups around it, so that is a secondary carbocation. And that's fine. It could happen, but it's just not the best. We want only the best. So there's our carbocation there. So I think that was good practice to go through to decide which position the carbocation needed to be at. But the other thing with mechanisms is that you know a lot about what you're trying to do because you can just look at the product, right? We know that the carbocation has to sit at carbon 3 because if we put our same numbering onto the product, the bromine has to end up on carbon 3 at the end of the reaction. The only way it can do that is if the positive charge is at carbon 3. So not only can you use your kind of deduction skills about deciding about the best carbocation, you can also use some detective work of thinking backwards in your reaction. Okay, I need the bromine to be able to attack carbon 3. So carbon 3 is the one that has to have the positive charge on it. And so since we've mentioned the attack of bromine, let's do our next step, because I forgot to draw out, this is one of our intermediates, but I didn't draw out the other one. I was too excited about carbocations that I forgot to draw out our Br minus anion. And there's all of its lone pairs of electrons. So let's use that as our nucleophile to reach out and attack at carbon number 3 to form a new carbon-bromine bond. And then we get to our product and we're done. So not too bad, right? Since we went through the steps multiple times together already, hopefully this doesn't seem too challenging. If you still feel like, I'm not sure I could do that for myself, definitely please draw this out to practice. And I will also recommend revisit this slide and then use each one of these molecules, and you can draw through the mechanism for each of those compounds with HBr so that you can get some practice on your own. Now, these aren't necessarily mechanism questions because I didn't give you the products. But what this will allow you to have another chance to do is to predict what the products of a chemical reaction of, say, this alkene and HBr would be, right? So that's the next type of practice problems or questions that I could ask you on an exam are PTP and PTR type questions. So we'll focus on the PTP first. That's predict the products. So that just means I'll give you some kind of a starting material. I'll give you some conditions under which we treat it. And then you have to tell me what the heck is going on. What's our product? So let's go ahead and try this first one. Thinking about we need to add to make a carbocation that's the most stable, and then we need to add the halogen atom to that most stable side. So for a predict the product type reaction, you don't have to draw the mechanistic steps. If that helps you to understand where the hydrogen is going to add and how that carbocation is stabilized, you're absolutely welcome to do it, but you don't have to in order to answer this question. So I'm going to just analyze this without drawing the carbocations to practice this in maybe a more quick and concise fashion. So let's look at both ends of this alkene and see if we can sort of determine which one would make the more substituted carbocation without actually drawing it out. So of the two ends, we have this end down here in kind of light green, and we'll do this end up here at the top in darker green. If you think about what's at the top here in darker green that isn't drawn in, it's two hydrogens, right? So that top green carbon has two bonds to hydrogens, and then it has one bond to this carbon down here. And then if we think about the bottom carbon, we have a group here, and we have this carbon up at the top. So as far as looking for more carbons, it definitely seems like this bottom green carbon has more carbons around it already. So that's probably going to make the most stable carbocation. And again, feel free to draw that carbocation intermediate out here if you'd like. I'm going to just say, okay, I know that the carbocation wants to sit at this position, so I know that the halogen atom is also going to attack there. And so this is just doing a little bit of shorthand abbreviating and not drawing out the full mechanism in order to predict this product. So I know we're going to retain all of those carbon atoms there. I think that the carbocation is going to happen at this position and that the chlorine is going to reach out and attack it, and that will be our final product. Again, I haven't drawn in that hydrogen that's getting added as well, but it is still there and it contributes to being one of the three hydrogens on that methyl group. So that's what I mean when I say predict the product. You don't have to draw through the mechanistic steps, you just have to tell me what the answer is after the reaction is all said and done. Let's try this next one. So try this cyclohexene molecule with the addition of HI. Go ahead, pause the video here quickly and draw a predicted product for what you think is going to happen with this reaction. So we can do that same analysis about where we think a good carbocation might be. I'm going to draw the hydrogens here on either side, just as a little placeholder to help remind us. So if we look at this top carbon here, we have kind of this part of the ring and a hydrogen, so that hydrogen doesn't count. We only have one carbon group around. And if we look at the bottom, well, it's pretty similar, isn't it? We have kind of that carbon from the ring and the hydrogen, which doesn't really help stabilize at all. So both of these only have one carbon group nearby. So they're going to be equivalently stable. So it really doesn't matter which carbocation we form. We could form either one and they will end up being identical. So I'm just going to randomly choose to form the carbocation at this top carbon, but again, it doesn't make a difference. And if I form a carbocation there, I'm going to attach that I to that position. So that's the product of this reaction. Did you get it right? We'll have plenty more predict the products to work through and practice on your homework, so stay tuned for more of those if these feel a little bit tough or uncomfortable. The last type is the predict the reagents question. If you are asked to predict the reagents, that means that I will tell you what you're given and where you're trying to go. You need to tell me, if I were to go into the lab and do it, how would I do it? What reagents do I need? So if we know that we're in the category of adding HX across an alkene, and you're given an alkene, you just need to tell me what HX I need to add to this to get the desired product. So if we take a clue here from the fact that we've added a chlorine atom to this in our product, then we probably need the chlorine-based HX acid, which is HCl. So that's a fairly simple example of predict the reagents. Sometimes these can have multiple steps, but they probably won't until maybe the 4th unit at earliest. So that's how a predict the reagents type question might work. And so with that, we've had a little bit of practice here, and there's definitely still more things that we should be thinking about to review and practice as we go forward. If you felt a little shaky on identifying nucleophiles and electrophiles or drawing arrows from the previous unit, definitely go and practice that now. If you are, say, out of practice problems and you feel like you need some more, just ask me, send an email, and I can find some more for you to practice with. The next part that's a little bit newer is making sure that you feel comfortable with deciding what's a more stable carbocation and knowing how it's going to be formed, because that's going to be the really big, difficult part of this reaction. It's not so much, oh, okay, the halogen has to attack. We know that that's not too bad, but finding those carbocations and making sure they're stable is the trickiest part of this type of reaction, in my opinion. So we want to make sure we're really comfortable with that. And if you already feel really comfortable with all of this, you can go ahead and start looking forward to our next reaction, which is going to be the addition of water to alkenes. It's going to take on a very similar mechanism and pattern as what we just looked at, so it shouldn't be too big of a leap. But the thing that might be a little bit of a leap is looking at these rearrangements that are going to be another way for us to help stabilize carbocations. We didn't discuss today, and we'll talk about it next time. So if you have any questions about any of this, feel free to post a comment, send me an email, stop by office hours, or post in the discussion forums. Until then, take care.